They're all good. You guys good? Yeah.
Oh, Taylor's saying no.
All right.
Yo, my whole family got quarantined.
Oh, that's terrible.
Yeah.
Yeah.
All right. So let's see. There we go. All right. So looking at what do I do with that? What do I do with that paper? I don't have questions on it. There it is. Looking at question number 2, it says, we're on problem 3, question 2. It says, draw a free body diagram and explain the physics behind how to help explain the phenomenon. And there are 3 forces acting on each person. All right? Gravity, friction, and the normal force. All right. So if I drew out the free body diagram, you have 3 different options. Actually, I'm going to show you the one I printed off. All right. So if you just drew this first one, that would have been perfect. Okay. Since the guy was on the wall. Since the wall is right here, that's why the normal force is going that way, right? And then the force of gravity is going down, and the force of friction is actually holding you up, right? Because if the force of gravity and the force normal were the only 2 forces acting on you, you would fall down, right? So there had to be a force going up to keep you in place. That force going up is the force of friction. Okay. Any questions on that? How'd you guys do on that one? Might have been hard to draw on Google Classroom, but pretty good. All right. And then number 4, you guys saw the video, skateboarding one. They go in a circle. All right. Watch the video and notice the point at which skateboarders struggle the most to remain on their boards. Even though it seems to be the easiest part of the loop, use your knowledge of physics to explain what is making it difficult. All right. So when they're going around the loop, let's say this was the loop. The hardest part was like right there, right? They would go around, and then they would actually, well, I guess like right there. They would fall when they got back to the bottom. Why? Yeah.
How hot? Or because of the acceleration, there was a lot of acceleration.
Oh, okay. You can say that. The other answer? Yeah.
Possibly because when they're going around the loop, the acceleration was like tangent to the circle until it got to the very end when the motion came out of the circle, and the direction of the acceleration changed relative to how they were positioned.
So if I'm picking up what you're putting down, the acceleration, so let's say this was my loop and here's leaving. So right here, like the acceleration, you're saying centripetal? It goes in the middle, or are you saying it goes out?
I thought it went toward outside because it goes
In this case, it would be centripetal.
Oh.
Where in then
Except that when you get to the end, when you get out of the loop, it doesn't go towards the center anymore. Like it sort of changes direction relative to how they're moving. So
right.
The change in the force that's applied to the person skating would throw them off the board.
Very good. Very good. All right. The one I said is at the bottom. That's where you're going to experience the most G-force. Okay. That's one where you're going to experience the most G-force. Okay. And when you experience a lot of G-force, it's hard to even stand, right? Let alone be on a skateboard. All right. How do we feel on this? Feel pretty good? Any questions on this activity? All right, I wanted to knock that out real quick. Do we feel all right? All right, everybody should have that turned in and done. I will get that graded probably sometime soon. All right. I wonder how I can get rid of those X's. Oh. Maybe the eraser tool might help. Sweet. All right. So next, I want to go over Angular UCMs. All right. So I did create some guided notes so you don't have to write down the questions. All right. I was feeling generous. And I even hole punched them because, you know, our copier does that. Found out. I know. But wait, you don't need this?
Yeah.
All right. Getting fancy on me.
I like having everything in one place.
Fair enough. There you go. All right. So I'm going to go over maybe one or two examples that we're going to try one on our own. We'll be done. Learn about the planets for a minute. If you guys want to go above, you guys can look up like Kepler's law. We won't get into too deep Kepler's law. All right. So we're gonna hit some of this real quick. We'll be good to go. All right. I'm going to take that down a little bit. You guys want to learn about some half-lives?
Heck yeah, Mr.
No.
Bowers.
Half-lives? That's some good stuff right there.
That was the easy part of them.
I don't remember a single thing from Tim. I remember it being easy, but I don't remember a single thing.
No, it's not possible.
Yeah.
All right. So if we go back to this slide, I'm going to go back to this slide. Remember, when you're at the bottom of a hill, ooh, first try.
Are you gonna get back down?
Jumping.
Oh, okay.
All right. So when you're at the bottom of a hill, all right, our force normal is going to be positive minus mg, and our mass and acceleration are still positive. However, when you're at the top of a hill, all right, your acceleration is going to be going down, or it's going to be negative. Your acceleration is going down. And that's why we have a minus mv squared over r. You guys remember that? Yes.
Are these the same equations that we would use in algebra?
I mean, kind of. Yes. Depends what it's asking.
Okay.
All right. And then tension, we're not going to really cover tension. Okay. Well, I mean, angular is tension. We'll get there. All right. All right. So just a review, just so you guys kind of understand, when you're on the top, acceleration is negative. All right. So I have one example, more vertical, I want to go through, and then we'll be good. Okay. Then we'll get into angles. So if we look at number 9, all right, 9. It says, while driving along a country lane with a constant speed of 17 meters per second, you encounter a dip in the road. The dip can be approximated as a circular arc with a radius of 65 meters. What is the normal force exerted by the car seat on an 80-kilogram passenger when the car is at the bottom of a dip? Okay. So if we look at this type of problem, all right, when we look at this type of problem, we're still using, oh, there we go. That's not sure. There we go. Oh, no. Come on, 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 come on. There we go. Oh, you didn't see that. Wow, you got some quick memory right there. When you, man.
Did you use same things in the middle of it? Or just the
Just the end. Okay. All right. So I'm gonna zoom out a little bit. All right. So if we look at this type of problem, I'm actually gonna go full screen here. All right. My equation is gonna be force equals mass times acceleration, right? Force equals mass times acceleration, centripetal acceleration, right? So what's all my forces acting on the car seat? Between the car seat and the person. Force normal and gravity. Okay. Force normal and gravity. All right. Is equal to mass. What's my centripetal acceleration equation? Have we got that down yet? Centripetal acceleration. Velocity.
Velocity squared over radius.
Ooh. Velocity squared over radius. Very good. And we should have all our data. Right? We should have all our data. We know that force normal minus force of gravity is mass. So mass is 80 times acceleration due to gravity is equal to mass, velocity squared, over my radius, which is 65. We have all our numbers.
Would it be negative 9.8?
I think it's at the bottom.
When it's at the bottom, no, it's positive.
Okay.
Okay, and let's plug this in. Okay, we got 17 squared. Okay, I got my answer to be 1,140. So you guys again?
That's not the answer he said.
It's not. You want to know why?
Why is that?
Because the answer key's wrong.
You do that just to trip me up.
No,
Oh.
the answer key's usually wrong on here. 2 reasons. One, they always use gravity as 10 on here.
Why?
Did you make these books?
No.
Who'd you steal the slideshow from?
Who?
Yeah.
I don't steal them.
Who did you plagiarize
I
from?
don't plagiarize. I have a license to use them.
You're paying.
This is copyrighted material, Mr. Miller. Says it above the screen, above
This is
Physics burns. That's very good. That is. All right. So that's vertical. Okay. So we started horizontal. Horizontal was, there's only one option, right? Horizontal. Vertical is a little more challenging. Let's rock and roll to angles. Okay. Angles. We got this. So we're going to skip that one. We're going to skip that one. All right. Conical pendulum. All right. So a conical pendulum is a pendulum that sweeps out in a circular motion rather than just making a linear path back and forth. Okay. Have you ever seen the painters? There's people that paint using this now. Like well, like this actually.
It's just lazy.
What's it say?
Is that singing?
Might possibly.
Actually, really cool. It's kind of mesmerizing, honestly.
there is no.
Kind of hard to see. You guys should hold it.
Looks like it's real time.
Okay, we could just watch this all day. All right. Or I can just keep playing that. That'd be fun too. All right. So, if you look, all right. So force of Ty is equal to mass times gravity, right? So force of tension in the y direction. Okay. So force of tension in the y direction is equal to mass times gravity. Force of tension in the x direction. Where'd my piece of paper go?
Gold. Bye, buddy.
Thank you.
That was weird. That was a weird exchange. I'm like, do I take it? Like, I'm not.
No, that
I'm
was-
not a teacher.
I was like, dude, he just gave it to you. I was like, that's cool.
I'm like, okay.
But anyway, so force of tension in the y. So going up and down, right? So if I go over and down, force of tension in the y is equal to the mass in mass times gravity, right? However, force of tension in the x is the centripetal force, right? Because force of tension in the x, that's where it's going, right? If it's pointing towards the center, and that's what these equations are telling us. Does that kind of make sense?
Are we taking that?
Absolutely. If you would like.
The way that you just scared the heck out of
You can
me.
take a nap, dude.
Miss all this learning.
It's up to you. I just want to hear it one more time. Absolutely. All right. Now, I'm going to go over one example with you guys. You guys are going to try one on your own. All right. So, a 1.45 kilogram ball is suspended on a 0.8 meter string and swings in a horizontal circle at a constant speed such that the string makes an angle of 14 degrees with the vertical. All right, draw a free body diagram of the mass. What is the tension of the spring? What is the speed of the ball? Okay. So, there's a lot of questions on here. All right. I'm going to draw a free body diagram real quick of what we know. Okay. What do we know? Actually, I'll just use this guy. So, zoom in a little bit. All right. So, from the center, we know this is a 14 degrees. Right? We know that's 14 degrees. Let's see. We know the length of my string to my mass. Let's say this is my mass over here. There's my mass. We know the length of the string is 0.8 meters. Okay, so we know the length of this string. Okay. Let's see, what else do we know? All right. Length. All right, that might be all we know. 14. We know the mass of the ball. Okay, so we know the mass of the ball. So can we calculate the force of gravity? Can we calculate the force of gravity? Okay. So the force of gravity is mass, which is 1.45 times 9.8.
How do we know when to use negative 9.8?
The only time you would have used the negative 9.8 was when you're on the top of the hill.
Okay.
That's it. All the other times you're going to be using positive. Okay. Anybody plug that in your calculator? What'd you get? 14.21. Now, one thing you might know, one thing you know now is mass times gravity. We just solved force of tension in the y direction, right? We just solved force of tension, okay? So we know, I'm going to draw this going up. We know this is 14.21 now, right? Let's see, what else can we solve for? Well, we can solve for F, force of tension in the x direction, right? We can solve for the x direction. So we can either solve using centripetal force, or we actually know, what all do we know? Let's see. We know this to this is 0.8. We know my force, all right? So let's see. There's holding. Force of T of x makes the ball move in a circle. So force of T of x is equal to the centripetal force. We already have that up here. I'm just rewriting it. Oh, I can't see that. We already have it up there. I'm just rewriting it down here. Okay. Force of Tx is equal to centripetal force. Now, what I'm going to do is I'm going to create in a little equation to get Ft of x. Okay, Ft of x. So that's up here, right? That's Ft of x. So in other words, if I look at this, the tangent of 14. So if this is 14, this is 14. Does that make sense? If this is 14, that's 14. So the tangent of 14 is equal to opposite Ft of x over my adjacent 14.21. Does that make sense? So tangent of this angle is equal to the opposite over the adjacent. Okay? How do we feel on that? All right, I'm going to plug that in real quick. Tangent of 14 times 14.21. Okay, so I got Ft of x to equal 3.54. Okay, I got Ft of x to equal 3.54. Okay, how are we feeling so far?
Not here.
Terrible. Now, if that is equal to centripetal force is my mass volume squared over r. Okay. So if I look at this, all right, my mass, let's see, my mass is 1.54.
1.49.
Or 1.45. I'm at 1.45. And my, we don't know the other thing. Well, we can get there. Okay. So, that's about a decent amount of what I know. Right? So to answer B, it says, what is the force of tension? Can I solve for my hypotenuse to answer B on our problem? How can I do that? Pythagorean theorem, right? A squared plus B squared equals C squared. So I know 14.21. I know 3.54. So what is the tension of the string? 3.54 squared plus 14.21 squared. Square root of that answer. I got, this is going to be see, plus 4. Whoa, you're gonna add those 4 with 4. So you need 4 decimal places. Whoa. Okay. So that's the force of tension on the spring. So we had to find our string. So we had to find our y, we had to find our x. Did we have to find our y and x? No, we could have found one of them since we know the angle, right? But we do need our x for the second part, okay? So that's how you do B. C says, what is the speed? So we're actually kind of already working on the speed up here, right? We have our f of t of x, 1.5 v squared over r. Now r, how can I solve for the radius of, so my radius is technically here to here, right? You guys guess? Yeah.
You just do the sine of 14.
So- Say that one more time.
The sine of 14 times the length of the hypotenuse.
Yeah. Very good. All right. I was gonna put it out a little bit. 0.8. So the length of the hypotenuse is 0.8. So you're gonna multiply by 0.8 on both sides, so those two cancel. Yep. So r is 0.8 times sine of 14. Okay. Does that kind of make sense? 0.8 times the sine of 14. All right, so I got r to be 0.194, and now you can solve for v. What is my final answer here? What is my final answer? Anybody get an answer? We got about 0.687. So we got.
Did you? Oh, then you have to square root that. That's equal to b squared. Have you done that?
3.54 times 0.194 divided by 1.45. Take the square root of that. Yeah.
It should be like 0.826.
I got 0.6.
I got 0.6.
I got
That's what I got. That's what I got.
Okay.
Yeah, 0.649.
You said 7, I was like,
Oh, my bad.
Oh.
Okay. Now, the next problem. I want you guys to try out on your own. Okay? Now that you know, you're using the same stuff we know, but now we're throwing in angles. All right? I want you to try out number 13. Okay? It's going to be a little tricky. All right? And when you guys get a firm grasp of what you think it is, you are done for the day. Or if you don't, try to get it done tonight. A 2 kilogram mass hangs from a string, forms a conical pendulum. The period of the pendulum of the perfect circle is 1.4 seconds. So we know the time
What did I just notes from yesterday?
Yeah, we went over. Yeah. Right. So we know the time, we know the velocity. Two key things right there. So far in this chapter, we've used that one. Which is the same thing, right? Total force, velocity squared over r. Triple acceleration, velocity squared over r. And, you know, where we go. How can you use those equations to your advantage? How can you use that information? Hopefully you know the force of tension in the y is equal to the force of gravity. So you should be able to solve that pretty easily. How can you solve the force of tension in the x? Because then you have your x, you have your y, you can easily solve for theta then. How can you solve force of tension of x? Yeah. Bless you. Okay, I can go over this real quick. So, since we're trying to find the force of tension in the x, well, we know force of tension in the x is equal to my centripetal force, right? Okay, So my centripetal force is mass times velocity squared over r. I'm given my mass, which is 0.2. Okay. Let's see. My velocity, I'm given my velocity at 2 meters per second. So what's 2 squared? And to find r, you have to plug it in this equation. That will get you r. And then you'll just solve it. Okay? So you're gonna solve for r right here. Plug it in over there. Guys, have a fantastic day. We'll see you guys tomorrow.
Would Vaughn Nugent please come to the receptionist desk? Vaughn Nugent?
Have a good day, Mr.
You
Bowers.
too. That kind of makes sense
I think
a
so.
little bit.
Very well, technical.
The final
And Mr.
answer
Bowers.
is 40 to 42.
40 to 42.
Yep.
I've got 5.
Have a good day, Mr. Bowers.
Oh, wait.
See ya.
Oh, wait.
What were the answers to that question?
So the angle was 42. Sig figs would have been 40. The other answer is 2.64. is what I got.
Okay. Thank you.
Yep. Did you guys figure out how to do it?
Mhm.